Yo, what's up everybody? It's your boy, Mr. Cuitino. Today what we're going to be doing is talking about Unit 6, Molecular Chemistry. Now this is going to be just the bare bones and what you guys really need to know for this particular unit. So we're just going to go ahead and jump right into it. So first we're going to talk about what the heck is a mole. So the mole is a unit of measure and it refers to how much of a specific substance you have. So let's say you have an example of a glass of water, and that glass of water has some amount of water in it. We don't necessarily know how much is in there. So we could make complicated measurements and write all these reactions that involve masses and trying to figure out exactly how much stuff is in there. Or we could very simply say that 1 mole of H2O has a mass of 18 grams. So if we have a glass of water with 18 grams of water in it, it would have 1 mole of water in it, or H2O. Now, the formula mass is very specifically the mass in grams of 1 mole of an entire molecular formula. Now, that is both compounds as well as elements. So you could have the molecular formula for an element, and that would be its atomic mass. And now we're going to get to that in just a second. The gram formula mass, sometimes referred to as the GFM, though you won't see this very frequently, because more often than not you're going to see this thing, molar mass. Molar mass is what you're going to see most of the time you're doing these particular kinds of problems. So what does this look like? We're going to just jump right into an example. Now, what I want you guys to note is that this should be, or it should read as K2CO3. We shouldn't have these numbers. These numbers here should be subscripts like they are up here. And that helps you identify how much of every particular thing you have. So when you have a subscript after a letter like this, after an element, it means that you have that many in that particular compound. So what we can do here is we can say, alright, there's this 2 after the K. That's telling me that I have 2 atoms of potassium. And the thing that you guys need to be careful of is here, this CO3 with the 3 after this does not mean CO3. Does not mean CO3. The parentheses will tell you where you need to actually do the multiplying of that number. Because there's no parentheses here, you're going to have 1 C and 3 O's. The next thing that you're going to need is the actual atomic masses of those elements, because that is the molar mass of the element. And we can use those in conjunction with all of them put together. So what we're going to do is we're going to find the particular elements that we need. So right here is K. So we're going to highlight this just to point it out to ourselves. So right here is K. And what I'm going to do here is I'm going to circle the atomic mass just so we know what we're dealing with. So K, and we're going to round this to 39. So potassium, or K, is going to have a atomic mass of 39. Then we're going to do the same thing. We're going to find carbon, which is right over here. Here is carbon. And oxygen. And we're going to highlight these again. We're going to round that to 16, and we're going to round that to 12. So now that we have those values, what we can go back and do is we can do the same thing that we just did, where we identify how much of everything there is. 2 atoms of potassium, 1 atom of carbon, and 3 atoms of oxygen. And we're going to multiply those times the atomic mass of that particular element. So potassium is going to be 39, carbon is going to be 12, and oxygen is going to be 16. So what we can then do is go ahead and set all of these equal, and what we're going to get is 78 plus 12 plus 48. And what you are going to be doing is just very simply adding all these numbers up. And we're going to do the math here, and we're going to find that overall, these add up to 138. Now, the units of this kind of problem is always going to be the amount of substance you have per mole. So, for this particular substance, K2Cr3, the formula mass of K2Cr3 will be 138 grams per mole. And you can abbreviate this to MOL. You can also write the E. It doesn't particularly matter. And here we can just come and double check that all of our math made sense. We have 2 K atoms, 1 C atom, and 3 oxygen atoms. And we're going to multiply those times the atomic masses of each. 39 for the potassium, 12 for the carbon, and 16 for the oxygen. And then we're just going to multiply all of those together to get our final answer in 138 grams per mole. That is the formula mass of this substance. Now, I'm no longer going to show you going back into the reference table to look up these values. This is critical practice that you guys should get yourselves. But what I'm going to do is I'm going to continue to go through these kinds of problems. And I'm going to start again by redrawing this under the correct format. So this should be Li2SO4. So we can start to correctly identify how much of everything we have again. So over here I'm going to say I have Li, I have S, and I have O. How many of each do I have? Well, I can see from my substance here that I have two Li's. So I'm going to say, okay, I have 2 of them. I'm going to put that right here. 2 Li's. I have 1 S. And again, be careful, there's no parentheses here applying that 4 to the entire thing. It's kind of just like distributing. So we're only going to have 1 S, but 4 O's. We can then multiply those times the molar mass of the element, or its atomic number. Atomic mass, sorry, not atomic number. Just to be very clear. When we're using the atomic mass of these substances, not their atomic number. So we're going to have 2 times the atomic mass of Li, 7. 1 times the atomic mass of sulfur, which is 32. And 4 times the atomic mass of oxygen, which is 16. We're going to multiply these things out. 14, 32, 64, 64, and then simply add all of these up, like so, plus, plus, and we will get our final answer, which should be 110, and then we have to put the units on that. The gram formula mass of this substance is going to be 110 grams per mole. Let's do another example, and again rewrite it the way it should look. So we're going to have Ca, and here we finally have our first parenthesis. Now that parenthesis is saying that this 2 right here, is applying to this entire package, or bundle, or polyatomic ion, however you remember what that is called. So when we go to decide how much of everything we're going to have, we're going to say Ca, O, and H, because that's what we're dealing with. And we're going to say, alright, how much of each one do I have? Well, we can start to find out by saying this Ca does not have a number behind it, so that means there's only going to be 1 of them. So 1 Ca. This 2 is being applied to the O and the H. So we're going to have 2 O's and 2 H's. We can then multiply those times their atomic mass, or the molar mass of that element. And you're going to see that Ca is about 40. Again, if you're ever confused about where to round, try to just round to the nearest whole number. oxygen is going to be 16, and hydrogen is going to be 1. Multiply these out, we're going to get 40 plus 32 plus 2. And when we add all this up, you're going to get that the molar mass of this substance, calcium hydroxide, is going to be 74 grams per mole. Let's do one more example before we move on into our next section. So here we have, once again, another parenthesis that's telling us that there's a polyatomic ion there. So we're going to have BaNO3, 2. Now this 2, again, is going to be applied to the entire polyatomic here. And these things do sort of stack up. So this 2 is going to be distributed to this O3 and the N. That means when we go out to write how many BAs do I have, how many nitrogens do I have, and how many oxygens do I have, you're going to have to consider that this is 3 oxygens times 2. That means that we're going to have, very specifically, 6 oxygens. So I'm going to write that right here. 6 oxygens, 2 nitrogens, and only 1 barium. We go to our reference table to look up the molar masses or the atomic masses of these substances, and we find that barium is going to be 137, nitrogen is going to be 14, and oxygen is going to be 16. Again, we just simply multiply these out and add them up, so 137 plus 28 plus, which should be 96 if my math is correct. And overall, that should give us an answer of about 261. Let's not forget the units. The gram formula mass of this substance, barium nitrate, is going to be 261 grams per mole. Now for this particular problem, we are finding the molar mass of this substance. But this substance is a little bit weird and a little bit different from what we've been seeing before. What I'm going to start by doing is write out how this should actually look with all the proper subscripts and all of those things. The substance we are dealing with is magnesium bromide with what is called a hydrate. So this particular substance is going to be hydrated. Now what do you think of when you say hydrate? Well, water. And that's exactly what this means. This salt or crystal substance is going to be hydrated. Water is going to be mixed into its crystal structure. Now, how do you do this kind of problem? When you want to determine the molar mass of this, you can almost treat this guy here as if it were just a plus sign. So you're going to have these two things together and you're going to solve out the entire thing. Now, something we haven't seen too much of that I want to point out is that when you have a big number in front of the entire compound that you're dealing with, that 6 is going to be distributed to this entire H2O. Kind of like this. Just so that we can be clear about how this sort of thing works here. So when we go to write out, we're going to start by identifying every element. That's an ugly M. Mg, Br, H, and O. How many Mgs do I have? That one's easy. I'm only going to have 1 Mg. How many Brs do I have? Again, there's nothing more complicated really going on here. So you just know I'm going to have 1 Mg, 2 Brs. Now this is when it gets a bit tricky. This 6 is going to be distributed to this O. So we're going to have 6 O's. And again, this 6 is also going to be distributed to this H2. So we're not going to have 6 H's, we're going to have 12 H's. But after this, we're not doing anything different. We're going to identify the molar masses of these elements, or their atomic mass. and multiply times how many of that we have. Mg is going to be 24, bromine is going to be 80, hydrogen is going to be 1, and oxygen is going to be 16. Now we're just going to set all of these equal and then add them up just as we have been before. It's going to be 24 plus 160 plus 12 plus 96. And if we add all of these up, hopefully my calculations are correct, but we're going to get about 292. And that is going to be the molar mass, the molar mass of this substance. This thing is called a hydrate, and we're going to see that in just a little bit. But we're going to want to include our units down here. 292 grams per mole. Let's go back to another easier example where we don't have that other stuff going on. We're very simply just going to have Al, OH3. Careful of how you're distributing this. We're going to say Al, OH. We're going to say how much of each one do I have? Well, I only have one Al, one of those, 3 O's, and 3 H's. Then I'm going to say, alright, what are your atomic masses? Atomic masses, or their molar masses. Aluminum is going to be 27, oxygen is going to be 16, and H is going to be 1. The more you see these, some of them, like oxygen, you're just going to end up remembering. Multiply them all out. 27 plus 48 plus 3. And your overall answer here is going to be 78 grams per mole. And that's going to be your molar mass for this substance. Now this one is written in kind of a tricky way, mostly because the formatting on this PowerPoint sort of gets messed up. But what we're going to actually be looking at is our good old friend glucose, which is C6H12O6. And we only have one of these, so when we go to identify how many C's, H's, and O's I have, you can just very simply take the subscript here of these guys. You're going to say, well, I'm going to have 6 C's, 12 H's, and 6 O's. So I'm going to come down here and write that out. 6 of these, 12 of these, and 6 of those. And just for the sake of consistency, I'm going to do these in red. 6 C's, 12 H's, 6 O's. Then multiply them times their molar masses, or their atomic masses. Carbon is going to be 12, hydrogen is going to be 1, and oxygen is going to be 16. Multiply these out and add them up. 72 plus 12 plus 96 is going to lead you to your overall answer, and what we're finding here is the molar mass of this substance, which is going to be 180 grams per mole. Here's one more example where we have this sort of weird hydrate crystal thing, and again we're going to get to these in just a sec. I'm going to rewrite this out just to make it clear how this works. We are going to have CuSO4, and then you can almost pretend this is a plus this 5H2O. So we're going to do CuSO, and what I'm actually going to do here is I'm going to keep this particular O right here, this one. I'm going to keep it separate from this O. I'm not going to add them all up because that might make it more complicated. So what I'm going to actually just go ahead and do is I'm going to then do H and O. This is going to help you from getting confused, because if you do too much all in one thing, it's just going to end up messing with your calculations. So I suggest separating it out. We're now going to identify how many of each of these we have, just like we've been doing. So you can start looking at your Cu. And you're going to say, okay, how many of these do I have? Well, there's no number in front or behind it, so I have 1. I have 1 S and 4 O's in this particular substance, because this 4 is only getting distributed to the O, nothing else. We're going to have this 5 times the H2 and this 5 times the O. So we're going to have 10 H's and 5 O's. We're going to multiply these times their molar masses or their atomic masses. Our Cu is going to be 64. Our sulfur is going to be 32. Oxygen is going to be 16. Hydrogen is going to be 1. And oxygen is again going to be 16. Then we're just going to go ahead and set these all equal. Multiply it out and add it up. This is going to be 64 plus 32 plus 64 again plus 10 plus 80 is going to lead us to our final answer of 250, which is the molar mass of this substance here in grams per mole. Now, percent composition is something that we started to talk about as part of one of our labs. The percent composition allows you to find out how much of one thing makes up your sample as a whole. And if you ever forget the formula, don't worry, it's in table T. Here's your formula. It's the mass of the part divided by the mass of the whole times 100%. So let's say that I'm taking a basket. Inside of that basket, I have a bunch of apples. Now, be amazed at how good I am at drawing. So here we have a bunch of apples that are red, and we're going to have 2 green apples in the mix. I could find out what portion of my sample is green apples. The way I would do that is by taking the mass of the part, or in this case, the 2 green apples that I have, so I'm going to do 2, divided by the overall number of apples that I have, so the mass of the whole. That's not how many are not green, that's everything together. So that's going to be my 6 red apples plus my 2 green apples, which is going to give me an overall number of apples of 8. So I'm going to put 8 down here. That's going to give us an answer of 0.25, and then we're going to multiply that times 100%. What this is eventually going to tell us is that 25% of the apples that I have are green apples. You can do the same thing, except with compounds. So what we're going to start to do here is we're going to identify how much each of these how much each of these elements contribute to the overall mass of your substance, and we're going to do that in terms of mass. You won't be asked to do this in any other form of measurement but mass. So we have to do the same thing that we've always done, where first we have to identify the number of each thing that we have. So we're going to write it out, NH4, 3 of those with 1 PO4. So we're going to say, alright, I have N, I have H, I have P, and I have O. How much of each of these do I have is then what you have to ask yourself. So we're going to do the same thing that we've done all the way up until this point, and we're going to say, alright, well, I can tell that this 3 here is being distributed to this H as well as this N. So I know that there's going to be 3 N's. This 4 times 3 is going to be 12 H's. This 4 here is not being distributed to the P because there's no parentheses around it telling you to distribute to it. It's only going to go to the O. So I'm going to have 1 P and 4 O's. So what I can then do is multiply this times these particular elements' molar masses, or their atomic masses, nitrogen is going to be 14, hydrogen is going to be 1, phosphorus is going to be 31, and oxygen is going to be 16. Multiply these all out and add them together. This is going to be 42 plus 12 plus 31 and plus 64. I'm then going to add all of these up, and we are going to get 149 grams per mole. Now, this is not the end of the problem. All we've done is discover the overall mass of this substance here. We still need to figure out how much each one contributes on its own. To do that, we're going to take this, which is the contribution of nitrogen, this, which is the contribution of hydrogen, this, which is the contribution of phosphorus, and this, which is the contribution of the oxygen. So what we're going to do is 42, and we're going to do this right up here next to this guy. So we're going to do 42 divided by the overall mass, which is going to be 149. Over here we're going to do 12 divided by the overall mass, 149. Here is going to be the phosphorus contribution, 31 over 149. And here we're going to do the oxygen's contribution, 64 divided by 149. Now all of these should be times 100%. Now I'm starting to run out of space here, so I'm just going to rewrite these down at the bottom. We're going to have the contribution from N is, the contribution from H is, the contribution from phosphorus is, and the contribution from oxygen is. And really we're just doing this math up here, 42 divided by 149 times 100%. You're going to find that nitrogen is 28.2% of the mass in this compound. Hydrogen is 8.1% of the mass in this compound. Phosphorus is 20.8% of the mass in this compound. And oxygen is 42.9% of the mass for this compound. And if you want to double check that you did everything right, if you add all of these up, they should add up to 100%, which they do. Now we're finally going to get a little bit more detail about these weird things that we saw before, this sort of thing called a hydrate crystal. Now a hydrate crystal is kind of just a crystal, which is a salt, and then it just has some amount of water in its molecular structure. The water's kind of just trapped as part of the crystal. So you have these things called the hydrate crystals, and then also have something called an anhydrous salt. An anhydrous salt is only a hydrate crystal that has lost all of the water, so it's just the salt that remains. And you can see here that we no longer have those moles of water as part of this compound. Now how much you have lost this water, there's a number of ways this could happen. Through evaporation, you could boil off the extra water, and you'd be left with just the anhydrous salt. So what you can start to do with this is do percent mass calculations with these hydrate crystals. So what we usually want to start with is identifying just the mass of what the water part is. And that's why I sort of kept it separate earlier, because it makes this part easier. So what we're going to do is we're going to say, alright, how many H's do I have? Alright, well, I have this 2H and I have this 1O. So what you're seeing here is the number of H's you have times the molar mass of that substance, the number of O's you have times the molar mass of that substance. The next step that we're going to take here is to find out the molar mass of just the salt portion. So what you're seeing here is the number of each of those that you have, 2 NAs, right here, times their molar mass, plus the 1 carbon that you have times its molar mass, plus the 3 oxygens that you have times their molar mass. So right here we have the Na, here we have the carbon, and here we have the oxygen. And you're going to find out that the salt portion is just 106 grams per mole. You can then continue this by saying, now how much does the entire hydrated salt crystal, what is its overall molar mass? So you're going to take the molar mass of the salt, and then you're going to take the molar mass of water and multiply it times the number of those waters that you have. So this is our second to last step. And then finally what we can do is calculate the percent composition of water in that entire hydrate crystal. We would do that by doing the same thing that we did with our other percent mass calculations. You're going to take what is the portion of the water divided by the overall mass of your substance. You're going to simplify your equation so that you have this 180, the portion of water, divided by the overall mass of your substance. You're going to get this answer here, 0.629, and you're going to be sure to multiply it times the 100% to get it as a percent. And you're going to find out that for this substance, sodium carbonate, hydrated crystal with 10 moles of water, is going to be 62.9% water by mass. So that's going to be how much this whole thing here is made up of water. Now let's look at a couple examples on how to solve these problems. What we have here is a much more complicated situation in terms of the wording, but the problem solving itself is not that much worse. So we have a 5-gram sample of this hydrate, CuSO4, and it was heated until only 4.3 grams of the anhydrous salt remains. So what we're seeing here is we're saying we had 5 grams originally, and when we got rid of all the water, because that's what anhydrous salt is, it weighed 4.3 grams. So we know that water was 0.7 grams, and I'm doing that by saying 5.0 minus 4.3 is 0.7. We know that's the composition of water by mass of this particular substance. So we now want to find out what percent that is, because we have a number, but the number is not really all that helpful until we actually do all the math out. So what formula are we going to use? We're going to use our mass of part divided by the mass of the whole times 100%. And what we're going to have is 0.7 divided by 5 times 100%. And that is going to be equal to 14.14 times 100%, or 14%. That is the percentage of water by mass of this particular substance. For our last example, we are going to have 3-gram sample of Na2CO3 hydrated with just 1 mole of water. So there's not multiple of these, there's just 1 mole. And it says it's heated to constant mass. This constant mass here is telling me that I have reached my anhydrous salt because no more water is leaving the system. And it wants to know how much anhydrous salt remains. So what we're trying to find here is what mass of anhydrous salt do we have left? So the hint here is find the percent composition of anhydrous salt first. So the way we're going to do that is we're going to say, all right, to find out what the percent composition of this is, I need to go back and do those math steps that I saw before. I have to say, how much Na do I have? How much carbon do I have? How much oxygen do I have? How much H? And how much O do I have? We're going to do this the same way that we've been doing it. I'm going to say, alright, I have to identify how much of each of these I have, so I'm going to go and I'm going to say, well, I can tell that there's this 2 applying to the Na. So 2 of those, 1 carbon, and 3 oxygens. Then over here I'm going to have 2 hydrogens and 1 oxygen because of this part right here. We're going to multiply these out times their molar masses. This one is going to be 23. This is 12, 16, 1, and 16. We multiply all of these out, we get 46, 12, 48, 2, and 16. We're going to add all of these up to get 124. Now that's the mass of the overall substance, and we're going to sort of divide this right here, because this part here, this is the H2O, and here, this is our anhydrous salt. So we can add up just this portion here on the top to find out what this particular mass is. So we're going to say 46 plus 12 plus 48 is equal to 106. And since we want to find out the percent composition of the anhydrous salt, we're going to say we have to take this, which is our part, divide it by the whole, which is going to be this 124 from down here, and multiply it times 100%. This is going to get us to a value which is 85. Let me move the screen over a little bit. 85.48. Now, do I have to be that detailed? Not particularly. So we can leave this here as this percent. I'm going to write the percent here. And then what we can do is we can say, now that I know that the anhydrous salt is 85% of the overall mass, I can multiply these things together. I can say 85.48% times those original 3 grams that we have up here. So this is going to be times 3. And when you multiply by a percent, typically you actually want to leave it in the decimal format. So this would actually be 0.8548 times 3. Overall, what this calculation is going to give us is this value, which is 2.56 grams. This 2.56 grams here is the amount of anhydrous salt that remains. Because after all the water here, after this water has been evaporated, you're going to be left with just the anhydrous salt. That about brings us to the end of this video. Keep in mind that if you guys have any questions, leave a comment in the comment section down below. Maybe I will get to your comment, or maybe one of the other people watching this video will have the answers to your question. If you guys like the video, make sure to hit that like button, and don't forget to subscribe. You don't actually need to subscribe.